So, okay, welcome back after the break. What I've done before the break, I put in here for the esoteric split. You remember this is the version of the in-place streaming that we use for the CPU version. I've pulled out these two pictures that depict the pre-collision and the post-collision part, where this, unfortunately, I'm colorblind, but I guess that cyanish thing here is the set A, and this orange here is the split B. Yeah, and they are distributed over these eight neighbors instead of the 26 neighbors, yeah, that are all going into positive direction. So, and the idea is that we split them in such a way that we read most of the data from the same node, so that we can read things together and write things kind of together. So we have 1, 2, 3, 4, 5, 6, 7, yeah, that we can read from this node. We have 4 that we can read from this node. Unfortunately, the only 1 that we can read from that node. So this is how we read it, and this is how we write them back. Yeah. So, and this is the picture that I wanted to show for the esoteric split. Now, after this, we come to a completely different topic yet again, but which is equally important, and this is the conditioning. The conditioning that we use in virtual fluids. Okay, I thought I had more time in my, where I say something, okay, let's say something very, very general. Yeah, you have numerical methods, and you can roughly say that they're explicit numerical methods and they're implicit numerical methods. And the thing is, lots of you deal a lot in their life with implicit numerical methods. And the way they are different is when you have an explicit method, you just have a function that you evaluate. So you know what you have to do. You have a function that you have to evaluate. And if you have an implicit method, what you do is you iterate. I mean, you also have function that you have to evaluate, but then you get to an approximation. And using this approximation, you iterate until you get to a result. So if you iterate until you get to a result, that means that you are assuming that what comes in has an error, and you don't actually care where the error comes from. So for example, if the error comes from round-off errors, then these round-off errors by iteration are, also removed, right? So this is why, so the round-off here is kind of part of what is here called the residuum, which you want to minimize, and therefore these, for the round-off, iterative methods are kind of self-healing. Yeah, so when the round-off errors from the previous iteration step, they go to the residuum and then they are removed in the next iteration. So unfortunately, this is not the case in explicit methods. Here we have round-off accumulation. So whatever you did wrong in the evaluation of your method, this will stay there forever, right? So, and therefore, this is kind of more dangerous here. Now we need, maybe we have many professors here, so maybe you already know everything about this, but maybe not everybody. Let's try to understand two problems that we have with round-off errors. I mean, one thing is for clear. We have the Lattice-Boltzmann method is an explicit method, even though we had in between this, we thought that it comes from an implicit method, but the algorithm is explicit, so round-off errors add up. And in particular, because the Lattice-Boltzmann methods, and in particular the cumulant Lattice-Boltzmann method, is not well conditioned, which, by the way, is one of the reasons why it was so difficult to actually implement it in the first place. So because the first implementation of the cumulant Lattice-Boltzmann method turned out not to give the results that were expected. And then it took a very long time to understand why this is the case. So you really need to be diligent with what you do numerically if you want to implement a cumulant Lattice-Boltzmann method. Yeah? That can take years to make it actually run. Unfortunately, or fortunately, I don't know. I mean, the thing is, I talked about the cumulant method for 8 years before, on conferences, before I published the paper, and nobody tried to steal it from me. I mean, that's really amazing, yeah? Okay. Because it didn't work. Okay, let's I mean, I must be very stupid that I've worked so long on a single problem. Okay, let's try to understand two different things. Two different things here, namely the data loss in storage, in how we store the populations. So remember that the populations Fijk, they are superpositions of some moments. Now they are not directly sums, yeah? They are not necessarily superpositions in terms of cumulants, because the cumulant transform is nonlinear. But for moments, for our moments, this is just the sum of the moments. So you can just write Fijk is some sum over A, B, C, and now it's the sum over A, B, C. You could have some value, some tensor alpha ij k a b c, so 6 indices into m a b c. So, and now this can be written as a transformation matrix, which is a constant. Yeah. So you can write each population as, the sum of these moments. And now let's look how we are going to actually store these things. They are stored, of course, in the floating point number. Now this looks now very, very basic, but you'll see the point why I'm telling you all of this. So let's remind ourselves what is, for example, how floating point numbers look like. There's a standard. Not all processors follow this, but IEEE 757. Now this is one possibility. Say we have one bit as a sign. Then we have 1, 2, 3, 4, 5, 6, 7, 8 bits as an exponent. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, I don't know whether this was correct, but let's get it that this is 23 bits. Say this is a 32-bit float. So in VirtualFluids, what you have to do is when you compile VirtualFluids, you have to set in CMake whether you want to compile it as float or as double, right? So this is the only versions that we distinguish, and then all the variables will be called real in the code. Yeah. So one possibility is you want to say now for the purpose of this discussion we are dealing with 32-bit integer. Okay, there, yes. Here, this is the fraction. So this is where the actual value is stored. So what are our problems? Let Nabla talk. So all the moments, because we store populations. This is important because only populations can stream. So we have to store populations, even if we use moments for the calculation or cumulants for the calculation. Yeah, we have to store populations, and therefore all the moments share the same space in the fraction. And now we have the problem that these moments come at different scales. And this becomes even more apparent for cumulants. Cumulants, because they are independent, in order 3 cumulant, yeah, is giving information on the flow that was not present at the lower order, yeah. So it is actually the next order in the cumulants, non-equilibrium cumulants, is asymptotically smaller than the previous one, right? And this is a problem. So something that you can learn from the full lecture, which I have not advertised, which I actually wanted to do. We'll advertise this tomorrow probably. When we analyze our code or the lattice-Boltzmann equation, what we have to do is we have to decide on a scaling between time steps and grid spacing, and the theory that goes from the Boltzmann equation to the incompressible Navier-Stokes equation actually only works for a specific type of scaling, and this scaling is the so-called diffusive scaling, where we assume that delta t is proportional to delta x square, and this we put into one smallness parameter epsilon square. Yeah, so this is the only scaling by which we actually see convergence to the Navier-Stokes equation, to the incompressible Navier-Stokes equation. So I heard that people are working on acoustics. So when you work on acoustics, you don't want to use diffusive scaling, because diffusive scaling puts the speed of sound to infinity while you refine your grid. So you don't actually see any acoustics. You can use acoustic scaling. There you see acoustic waves, and you can do actually acoustics with this. And Mr. Kutscher did some beautiful simulations of an organ pipe where you can actually hear the organ pipe, yeah, the sound of an organ pipe, and it was noted. I mean, and you could notice. My mother is an organist, yeah. So she told me this is this note, Yeah, and I mean it was not, and we 3D printed it. So the original version was only a plastic 3D print. They were of similar quality, I could say. Yeah, both of them were not really the excellent version. Yeah, but there was a very distinct tone that you could hear just from the simulation. So you can do acoustics, and this is often done with the lattice-Boltzmann method and also with the cumulant lattice-Boltzmann method. But then you have to make additional assumptions on the Mach number to actually see the convergence. Yeah. The real convergence to the incompressible Navier-Stokes equation only in diffusive scaling. So, and now let's analyze this. Let's see what this means for these for our populations. So there is a part in the populations that goes to epsilon 0. This is the density. And this is the zero order. So we write the asymptotic order to which we get the result, the asymptotic order to which something appears in the equivalent partial differential equation when you do the complete analysis. And here comes out rho to the zero order, and this is a constant. Meaning that to the zeroth order in grid spacing, the density is constant, which you would assume in an incompressible flow. So then you get something to epsilon 1. This is the velocity, meaning that velocity, if you refine the grid, velocity has to, the numerical value of the velocity needs to get smaller. Then pressure comes at second order. Second order. And also stress is at second order. And again, if you want to have a deep dive into this, I have to unfortunately ask you to go to our YouTube channel and watch the lectures on asymptotic expansion. So this is lecture 6 in the full course. Yeah. So you can listen 20 hours, yeah, on this if you're very interested. So yeah, just very briefly, the solution that you get, you get a U as a result of your simulation, and this is composed as a smallness parameter times U to the first order plus epsilon to the third order times U third, and then there is this infinite sum of other terms. And this, what we have here at the leading order, is our solution. And what's left is the error. Yeah, that's so we get U solution plus error. So this is actually the real thing. And with rho, the density, it's similar. We get rho 0. This is a constant. Then we get epsilon square, rho to second order. So this is up to a constant, the solution for the pressure. Or the pressure variation. And then there is error terms for this too. Error in pressure. And now, because this is a smallness parameter, we have epsilon to the order 0 is, of course, much larger than epsilon to the order 1, and which is much larger than epsilon to the order 2, and so on and so forth. So if we look into the fraction of our floating point number, say we have here the most significant bit. of the fraction. And here we have the least significant bit. And now here is the population is stored in this. And the population is the combination of all the moments, which are the solution of the Navier-Stokes equation, yeah, put together. So now what you have, what's defining the range of your number is the constant that you have here. This is this rho 0. This is in front of this. So then you have the velocity epsilon to the first order is here. Say, then this pressure epsilon to the second order, there's actually speed of sound in this, but doesn't matter. Rho second order, so this is the pressure. You also have the stress. That's also in here. So this is actually the derivative of the first order, which is the solution. And then you also have things that you don't care that much about. This is the ghosts. By the way, the ghosts apparently are not important, but if you do what I had in the previous lecture where we talked about the higher order terms that we have to set, yeah, they are inside the ghosts. So if you don't do the conditioning right, yeah, so you cannot do the other thing too, yeah, because they just don't show up in your solution. Now, problem being other color. So these are the number of bits that each of the quantities can actually use. So this is the effective number of bits available for each quantity. So, an example, even though it's stupid, but just to make it clear. Say rho to the zero order is 1. And say our velocity, or velocity with epsilon, is 0.01 delta x delta t. And then we'll have cs square rho to second order. Actually, we have an epsilon square here. So this is proportional to epsilon u square, which means that this, if your numerical value of the velocity is 0.01, the variation that you see in pressure will be of the order of 0.001. Yeah? So it's like square of what you have here. And this rho 0 is, of course, is largest and defines the exponent. So this means that rho 0 is stored in all 23 bits. So this epsilon u first, say this is 0.01, then if you write this in binary, this will be at the same, in binary with the same exponent. That's the important part. So what you get here is you get, say, 7 bits that are just 0. They are 7 bits lost. And then you get some numbers which are not important. 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0 binary. So I hope I just didn't do this incorrectly. So then the pressure epsilon square cs square rho, say this is of the order 0.0001. So this will be stored in 0.000000000000. So, you know, you have 23 bits to do this. You have 14 of them are lost. And then you have 110100000110b. Okay, now the question is a velocity of 0.01 as a numerical value, is this extremely small? Maybe not really. So in this example, where it's not really, it's just an example. In this case, 7 bits are lost at each order. And the number of the bits lost depends on the epsilon 1 term and how it compares to the epsilon 0 term. So the thing is, the smaller the lattice velocity, which is equivalent to saying the smaller the time step we have, the larger the loss in higher moments, and for this I mean, for example, pressure. Okay, now keep this in mind, what I've just been saying. The smaller you do the time step, the larger your error will be. Okay? Is this what your teacher told you? I mean, unless I was your teacher. Because I may also have told you in another place, the smaller you make your smallness parameter, the smaller you make your time step, the better your results. Now you have two things. You have asymptotics, which tells you smaller time step, smaller error. Now you have numerics on the other side, smaller time step, larger error. They are completely going opposite direction. Let's see how annoying this can be. Let's just think about a smaller velocity. And with a smaller velocity, I mean, smaller velocity does not necessarily mean smaller everywhere. Yeah? Saying you're interested in a small vortex that is inside a larger vortex. So, and now you're just looking at the relative velocity there, right? So, say you have a maximal, and you want to see what is the maximal ratio of largest to smallest variables. And by this, now I mean, which makes absolutely no sense, I want to represent my smallest variable by 1 bit. Right? 1 bit, I give 1 bit for the small variable. So this is 2 by the, I mean, it's the number of bits, 2 by the 23. So what is this? This is 8 million something, 8 million 3. So this is the ratio. That's the ratio that you can have between velocity and pressure in order to see pressure with 1 bit. So, for example, say we have a small velocity, 10 by the power of minus 4. Is this completely too small? Then epsilon square Cs square rho. So this is our pressure. This is 10 by the power of minus 8. This is much smaller than this. I mean, this is actually what we observed when Martin first, we have GPU. Yeah, actually we did this in 2 dimensions. Now we can simulate very large things. We can do convergence studies with very small velocity. So let's do this, let's run it, let's look at the pressure. And then Martin said, and now we're opening the pressure, and said, bam, this is the pressure. And I said, there is no pressure. You remember this? Maybe. Okay, I remember this. So, if you do this, then flows, even in 2D, this flows with velocity of this order, 10 by the power of minus 4, delta x by delta t. You do not observe any detectable pressure. Simply not possible. It's not. No variation in pressure. If you try to run this flow by pressure difference, of course, you're also in trouble, because the flow doesn't see the pressure either. Yeah. So now you have to do something, and what we are doing, we call this conditioning. Maybe some of the present professors are not completely d'accord with how I'm now defining conditioning, because it's of course special for lattice-Boltzmann methods. So rho 0. This is a constant. Because it's a constant, there is no need to store it. So this is the simplest measure that you can do, and this is done in VirtualFluids, of course. You define delta Fijk is equal to Fijk minus something that we call the weights. The weights is something that people who are using lattice BGK or single relaxation time methods know a lot about. So this is these are the lattice weights. So they are constant numbers, and if you sum over them, Ij and K, Wij, what you get is this constant out. Yeah. So if you subtract this, you just eliminate the constant. So, which sounds very simple, and everybody understands this. I just, I'll just draw it. I draw the picture again. Now you store delta Fijk. Now again, you have this here with least most. Least. Now, instead of what you had before, you store the velocity in the beginning here in the fraction. So this is a fraction, of course. So here goes the velocity, which means that everything that comes later also has more more space. Here coming the ghosts of third order. There are also ghosts of higher order. So again, now they have more space left. Zick. These are the effective available bits. Which is more. Okay, so this is easy to understand. There is something that's also easy to understand, but which I observe with students often not doing, and I know because it's annoying. The thing is, you're doing calculations with these populations. And actually, you need these populations sometimes in their original format for some calculations. And then you would actually like to go back to the original F. So you are tempted to add Wij to them. You have to remember, when you do this, you're losing everything. So it's not like you cannot do this sometimes. You have to do this all the time. Like in really always. When you do it once, it's gone. Right? So that's I mean this is the real problem, yeah? Because you cannot afford an exception, or there's only exceptions in very, very stringent conditions. So it is essential. I have to write this down because this is so important. It's essential that this well-conditioned state is preserved. I mean, this is if you add something to the code, yeah, you're responsible. This has to be restored due to all computations. Because the computations are, we have an what we have here, we have an explicit code, and therefore everything is a chain of computation. So the accuracy is limited by the operation with the least accuracy. Meaning that, okay, keep this in mind, a chain is as strong as its weakest link. Now you may notice why implementing this is not necessarily so straightforward. Yeah? So this is only one part of this. Yeah? So the part that is related to how you store data. But then you also do the actual computation, then you have data loss in computation. And then there's a question that I always ask my audience. So we do, especially if we compute cumulants, we do a lot of computations. Cumulants are pretty complicated, yeah? So what we do, we have some, not that many, but we have some differentiations, fractions. What is the divisions? But we have many sums and we have a lot of multiplication. Which operations are the ones that cause us the biggest trouble? What do you think? Who is for multiplications? Who is for additions? Okay, I can say you are much better than the Indians. No, not okay. That was very general. Like when I gave this at IIT Madras 2 weeks ago. Yes. So it is important to understand that actually multiplication is a relatively safe operation. Yeah, because the round of errors depends only on the least significant bit of the outcome. Whereas in an addition, the least significant bit, the round of errors depends on the least significant bit of the largest number at the income. The largest, not the largest number, but the one with the largest exponent. Okay, I wanted to write this down. Let me. So what's cause round of errors? You know, the longer I talk, the more I'm always writing from my script cheat sheet. So you get a result. Say you have a result. The result is an operation, and say there is that there is something going in first. There are two things that go in, like in a multiplication or in an addition, yeah? And they all have the numbers that go in and out, they have least significant bits. Here we have the one of the result, and here we have one that goes in and the other one that goes out. And now let us assume because we are talking addition and multiplication, we are talking about symmetric, so we can choose always that the larger one is the first one and the smaller one is the second one. Yeah. Assume without loss of generality that delta 1 is larger than delta 2. Then actually multiplication has an error in multiplication that is of the order of only the result, and addition is more complicated. There you get something that is related to the one that is the least significant bit of what is larger. So the problem being, if you have numbers of different size, which we identified we have, and you add them together, your round of error is defined by the larger number. Yeah, so the smaller numbers disappear. So we usually say that multiplication is safe, relatively safe speaking. And addition and subtraction is dangerous. Now, problem being that you remember that we wrote down these sums for computing moments, right? So actually computing moments is an integral, a discretized integral, so it's a sum. So what we do is we're computing a lot of sums. So we're doing what we are not supposed to do all the time in an explicit algorithm. Okay? Let's look, for example, when we want to compute this momentum here. Then this is the sum over ijk from -1 to 1 over I into Fijk. So now, I mean, very basically, you can write this as a loop or as 3 loops. Yeah? So this is the naive way you could do this. And then what you would do, you get a summation over n equal to 27. I mean, some of them would be 0 numbers. So the error that you would expect of these would be related to, okay, if you add up n numbers, you have n minus 1 additions, right? So it's n minus 1 times the delta, yeah, which is now the least significant bit, actually, of the largest one, yeah. Of the largest one between each of the two, yeah. But now for the purpose of this analysis, we assume that this is constant. Otherwise, this wouldn't work. So there is some theories how you can do summations better. There's a Kahn algorithm, so which you may know, but this is also expensive. There is one way of doing this, which is implemented in VirtualFluids, that uses the same number of operations that this naive summation would use, but is more accurate. And this is called the pairwise summation. So the original, if you look about pairwise summation in whatever, I don't know, Wikipedia or something stupid or less stupid, what you should do if you use pairwise summation, you should order your numbers according to their size. That would be a lot to do all the time, right? So this is why we use an ordering, a static ordering, which is not necessarily the best that we have, but we can do a little bit because we know that these populations are actually of different size because they have different weight and they are proportional to these weights. So this is why we pre-order them by lattice weights. So this is something that you usually, I mean, I don't know whether there are algorithms doing this, but we do this by hand. To keep values of similar size together. I have not found a way to get Mathematica to do this ordering, because if you Mathematica also orders sums, but it orders sums alphabetically. So actually all the sums we had to teach, I mean, maybe you can write an algorithm doing this, but usually it's not that much sums that you have to write by hand, so we write them by hand and sort them by hand. Yeah? So this is why when you look in the kernel, you'll find all these strange ways of computing these sums. So for our lattice that we are using, this D3Q27 lattice weights are actually, so we get the ones that are related to 1, 1, 1, right? It does not matter whether it's 1 or minus 1 or something. So all that have the same number of indices is the same. So this is 1 over 200. This is 26. This is related to the speed of sound, actually. W110 is 1 over 54. W100 is 2 over 27. And then we also have W000 is 8 over 27. So you see they are of different size, and we use this for pre-ordering them. Now let's see how would we now compute, or how does VirtualFluids compute M100. So there are several steps here, and we distinguish between these classes. So the class of populations that go with W111, so they can be written as F1, J, K, and what we do, we always subtract the one that goes into the opposite direction. F minus 1, minus J, and minus K. And you see there are, and now of these operations, there are 4 permutations. So we do this thing 4 times. Then there's a class W110. So of these we have F10K minus F minus 10K, and or the other way, F1 J0 minus F minus 1 minus J0. So they are actually the same number of operations of permutations of these. So they are all done in step number 1. And this class the class W100 is represented only once. This is F100 minus F minus 100. Here we do this only once. Now, after doing this, we add each of them together. This gives us step number 2. And then we add them together. This is step number 3. See, this is going like a pyramid now. Then we add these here together. This is step number 4. And in step number 5, we add this together and this leads us to M100. So why is this better? Because previously we had 26, 18, 17 actually. So the number of summons that we had was 18. So we add 18 numbers. Now the naive summation would therefore have an error of order 17 delta, whereas the pairwise summation would have not the error. Let's first say how many steps do we have. The number of steps that we have is the ceiling of the logarithm of 18, and this is 5. So the error that we have is of the order of delta log n, which is here 5, and this is smaller or equal to order of delta n minus 1. I mean, this is quite substantial. Yeah, we go from 17 times delta to 5 times delta in this case. Okay, so we tried to implement all sums in the code like this, and if you go into the code and implement something, please try to do the same thing. Yeah. So now we're coming to actually the important part of this conditioning business, and this is in the chimera transform. So the chimera transform was in a sense, this was the second Heureka moment in the cumulant method. So this is the point where the cumulant method actually started to really work. Before we had this numerical trouble was actually killing everything. So chimera is of course a crazy name because you have to give crazy names so that things get stuck. Yeah, I'll explain what it means. So first of all, the problem is that the cumulant method requires this transformation. So we have to compute cumulants, and the cumulants we compute from central moments, and computing the central moments itself is a big problem. So we go from the populations to central moments. And then we do the collision, and then we'd have to go from central moments to populations. In between, we also have to go to cumulants. Actually, this is at least what round-off errors are involved, is not that big a thing. For reasons that would take now a long time to explain, but the important thing is really the transformation from the populations to the central moment. So this is the big problem. Of course, you can do this in a naive way. I mean, there's in the beginning we've done this in an even more naive way, but so how would you do this in a naive way? You would just take the definition KABC and go over the sum I, j, k from -1 to 1, Fi, j, k, and this into I minus u by the power of A, j minus v by the power of b, and k minus w by the power of c. So what you have to do is you have 27 populations. That you sum 27 times to get 27 moments. So this is what you have to do. Forward and backward in each collision. Okay, now the way this is done, and this is kind of annoying. So the story is like this. When we published this, we of course had it in the paper, and we are talking about cumulants, including everything that, or most of what I've done before, and then this paper turned out to be 50 pages and has appendices going to I believe. And then the reviewer insisted that this chimera transform is so trivial compared to everything else in the paper that we should leave it out. And okay, so we left it in, I mean, just the equation we left, we didn't discuss anything, but I mean, we just say, okay, we do it this way. The thing really is, without doing this, it doesn't work. Yeah, and I mean for several reasons. First of all, it would be extremely slow, and it would be extremely inaccurate. So, what is the trivial idea about doing this here faster? And it's really trivial, but you see, good things are always trivial in the end, right? So we introduce chimeras, and the chimera is a part distribution and a part moment. Part is, okay, I'm stupid. Part and part moment. So, and then we simply do the following, and this is my stupid notation. I write now K as a central moment, ij, where I keep I and j non-integrated, and I integrate only over the third part, and I indicate this by this vertical line just because I didn't have any better idea. Yeah. So this is now only a one-dimensional sum, k from -1 to 1 f I j k k minus wc. So you still have to do this 27 times, right? Because you have to go through all the indices, and all of them have three of them. But each sum in itself only has 3 terms. Yeah, so you get this 27 times 3, and then you do the next dimension, BC. This is you sum over j from -1 to 1, and now here introduce k I j c. We are doing j minus v by the power of b, and this again goes 27 times 3 times. So, and lastly, we go KABC is the sum over I from -1 to 1, KIBC, I minus W by A, and this is 27 times 3. Now, if you add them up, you will be excused, and I thought this myself too, if you think that this is 3 times faster. I mean, it deserves to be done if it's 3 times faster. But the thing is, here, each term also includes more, you're summing over more things here. Yeah, so there are actually 4 things that you multiply. Here's only 2. Yeah? So actually, this is even faster than 3 times faster. And because this turned out to be too complicated to count, I let Mathematica count it. So I count the number of operations. So the naive one and the chimera one. So in terms of additions, we get 1,482. It doesn't sound, this is what you have to do when you do the naive summation. There are 270 in the chimera transform. Multiplications, very similar, 1,400. Oh, I think I got the wrong number because it was a very similar number. It was probably not I write twice the same. I remember that it was very similar, but it was not exactly the same. So I wrote the wrong number down, but it would be 1,400-ish. Yeah? And here we get 162. So this in itself, I mean, it's roughly one fifth of the number of the operations. And it's therefore also 5 times faster. And you have to remember this is the most expensive part of the entire algorithm. You make the most expensive part of the entire algorithm 5 times faster. That makes a hell lot of difference. And that is not the good part of it. Because the good part of this is that this now became, by this reordering, this now became a well-conditioned pyramid summation. And I've only analyzed this in empirically, but what we observe, so the empirical observation is we take some data from a simulation, we pick one point, we take this population, and we do a forward transform and a backward transform without any collision, and now we want to have the same thing back, right? And we do this for the chimera transform, and we do this for the naive transform. Yeah? And due to this difference in the conditioning of this, we see a big difference. So both of them lose data, but what we have observed, and this is really crazy, is that, I mean, it's only an observation. I have no proof, and I cannot say that this is always the case, but I have seen it in a single transformation that the naive transform lost 10 bits more in the fraction. More. I mean, say you have only 23, right? So the chimera transform lost 10 bits less than the naive transform. I mean, you can prove me wrong. Maybe I made a mistake and this was only empirical, but it absolutely makes sense from this perspective, because what we are actually doing is okay, so what we are doing when we compute moments, I remind you that the moments are obtained from the Laplace transform of the population. So you're doing a discrete Laplace or Fourier transform. Yeah, that's basically the same thing of this distribution function. This divide and conqueror is, of course, not a new idea. The divide and conqueror is the difference between a discrete Fourier transform and a fast Fourier transform. And the good thing with the fast Fourier transform is not that it is fast, but that it is much more accurate, because it is much better conditioned. It leads to much lower round-off errors, and this is exactly the same thing that we see here. So we replace the slow and inaccurate discrete Fourier transform by computing the cumulants or the central moments with a fast Fourier transform, which in addition to being fast, yeah, by means of first having ordered computations and by having much less computations, also has less round-off errors, and is therefore much more accurate and therefore much better to actually compute these cumulants, which are very ill-conditioned, actually, usually. Okay, so this is the end of section number 2. We will now continue with a discussion. I will stop the recording of this. I don't know whether we have recording. Okay, let me just first stop this.